Hi, and welcome to our background material. There are going to be three modules on background material. This is going to be the first one. It discusses arithmetic series and geometric series. So what's an arithmetic series? Consider a lengthened sequence of the form delta, delta times 2, delta times 3, up to delta times n. For example, you can consider the arithmetic series 2, 4, 6, and 8. That series is of length 4, therefore n is equal to 4. And delta is equal to 2. The first number is 2 times 1 is 2. Second number is 2 times 2 is 4, and so on. Now here's a claim. The summation of over n going from 1 to capital N, so that's 1 plus 2 plus 3 up to plus capital N, is equal to capital N times capital N plus 1 divided by 2. How do we prove that claim? So let me show you two different proofs. The first one is by mathematical induction. The basis case, take capital N is equal to 2, a length n series, and a summation over 1 plus 2 is obviously 3. And n is, the length is 2. N times n plus 1 divided by 2 is 2 multiplied by 2 plus 1 divided by 2. The 2 and the 2 cancel out. 2 plus 1 is equal to 3. 3 is equal to 3, so we have proved induction. Capital N equals 2. Can also prove capital N equals 1, of course. Can also prove a slightly larger n if you feel like it. Next, how do we complete an inductive proof? We take an inductive step where we assume that the property holds for capital N equals 2, 3, 4 up to capital N. And now we're going to prove that it goes from n to n plus 1. So let's look at a summation over lowercase n going from 1 to capital N plus 1. So this summation includes two parts. We're summing the first capital N numbers, and we have yet to sum the last number. The first capital N numbers, we're summing 1 plus 2 plus 3 up to capital N, and the next one. The first n numbers, their sum is n times n plus 1 over 2. And to that, we're adding n plus 1. Now, n plus 1 appears in both expressions, and therefore we're multiplying n plus 1 by half n plus 1. Or another way to think about that is n plus 2 divided by 2 is multiplying n plus 1. And that's what we wanted to prove. We wanted in our inductive step, moving to n plus 1, we wanted to show that the summation is equal to the number of elements, n plus 1, times the number of elements plus 1, n plus 2, divided by 2. So we're done. That's the first proof. Now there's also a second proof for arithmetic series. It's a well-known trick by the famous mathematician Gauss, that he was active in the late part of the 1700s and the first half of the 19th century. And when he was a kid in school, there's a legend, it's hard to know whether it's true, there's a legend that his teacher kind of didn't really like Gauss and wanted to kind of punish him. So we told him, go calculate 1 plus 2 plus 3 plus 4 up to 100. Now Gauss was, you can imagine, a clever kid. So after like 2 minutes, he's like, I'm done. Teacher didn't believe him. He's like, well, the answer is 5,050. So how did he do that? So let's change color. So Gauss was saying, well, what is 1 plus 2 plus and so on, plus 99 plus 100? So Gauss had an interesting observation. He said 1 plus 100 are equal to 101. 2 plus 99 are equal to also 101. 3 plus 98 are equal to 101, and so on. So next he said, okay, so every pair is equal to 101. How many pairs are there? The number of pairs is equal to the total number of numbers divided by 2, n over 2. And therefore, he said, okay, there are 100 numbers, n is 100, there are 50 pairs. Each pair sums to 101. 50 times 101 is 5,050. All right, so that concludes arithmetic series. And now we're going to move to geometric series. So instead of a linear progression, now we have a sequence of the form capital A to the power of k, a to the k plus 1, a to the k plus 2, up to a to the k plus n minus 1. Now, what's the length of this sequence? We're taking a to the k plus 0, k plus 1, up to k plus n minus 1. And looking at 0, 1, 2, up to n minus 1, there are n such numbers, and this is a sequence of length n. Again, we are interested in calculating the sum. To do so, let's put aside the k. Let's think about 1a squared up to a to the n minus 1. And let's simplify things further. Let's think about an infinite summation, 1a squared, a cubed, and so on. All the powers of a to the power of 0, 1, 2, and beyond. So that we'll define by psi 1. Psi 1 is a to the 0 plus a to the 1. A to the 0 is 1, a to the 1 is a, of course, plus a squared, and so on. Psi 2 is similar, except that the 1 goes away. So a plus a squared plus a cubed, and so on. Now let's look at psi 1 and compare it to psi 2. So first of all, every element in psi 1, when we move to psi 2, it's multiplied by a. 1 becomes a becomes a squared becomes a cubed, and so on. And therefore, psi 2 is equal to a multiplied by psi 1. The second observation is that all the elements in psi 2 exist in psi 1, and therefore psi 1 is equal to 1 plus psi 2. So now, combining this second observation, we conclude that, well, if psi 2 plus 1 is equal to psi 1, recall that psi 2 is equal to a times psi 1, and therefore a times psi 1 plus 1 is equal to psi 1. Or in other words, 1 is equal to, subtracting a times psi 1 from both sides, the right and the left-hand sides, 1 is equal to psi 1 multiplied by 1 minus a. And we conclude that, and this is in red for emphasis, psi 1 is equal to 1 divided by 1 minus a. Small caveat, a must be smaller in magnitude than 1, else the summation diverges. Even if it's equal to 1, we have a problem. Imagine the a is exactly 1. So 1 plus 1 plus 1 plus 1 plus 1, it diverges. So a needs to be smaller than 1. All right, quick example. Let's look at the infinite geometric series, 1, half, a quarter, 1/8, and so on. And let's sum those numbers. 1 plus a half plus a quarter plus 1/8, and so on. So a here is equal to half, and we're taking a to the power of 0 plus a squared plus a cubed, and so on. And we've seen that this summation is equal to 1 divided by 1 minus a. And a again is equal to half, so we have 1 divided by, in the denominator, 1 minus half. 1 minus half is equal to half, and 1 divided by half is equal to 2. Some of you may astutely think about it in a different way. Imagine that you're looking at the number 2, and you get a 1, and we've gone now half of the way from 0 to 2. You get a half, and you're going half of the way from 1 to 1.5 toward 2. We have the distance that's remaining is half, and we're now we're adding a quarter, and a quarter is again moving us half of the way. When we get to 1 3/4, we've moved half of the way from 1.5 to 2. So that's another intuitive way of thinking about these things. So we discussed 1 plus a squared, the infinite series. But recall, we're interested in a to the power of k plus a to the k plus 1 plus all the way up to a to the k plus n minus 1. And this is a finite length sequence, and it doesn't begin with 1, it begins with a to the power of k. So let's analyze this step by step, and we'll conclude with an example on the next slide. So a summation over lowercase n going from 0 to n minus 1, capital N minus 1, of a to the k plus n is equal to a summation over, well, what is a to the k plus n? It's equal to a to the k multiplied by a to the n. So let's just take the a to the k outside the summation. We have a to the k to the power of this expression in red, sum over n, lowercase n, from 0 to capital N minus 1 of a to the power of lowercase n. Now, this expression in red is equal to, so you have a to the 0, a to the 1, plus, here we have a to the n minus 1. All of these are in the summation. And then there are other values that are not in the summation, an, n plus 1, and so on. So what we're going to do, we're going to partition this into two parts. This part A is equal to the whole thing, part B minus part C. So we've partitioned B into A plus C, and this allows us to calculate the finite summation in part A. Okay, so the sum from 0 to infinity over a to the power of n, that's what I called part B, and the summation over lowercase n going from capital N to infinity of a to the n, that's what we subtract off in part C. And recall that part C is very similar to part B. It's a finite, it's an infinite geometric series. It's a summation over an infinite geometric series, except for one difference. Here we begin at index 0. Here we begin at index n. Therefore, this summation is multiplied by 1 minus a to the power of n. This summation we've seen before. It's equal to 1 divided by 1 minus a. And recall that we need one additional thing. We need to account for the a to the power of k. And in summary, the sum over a to the k plus n, where n goes from 0 to capital N minus 1, is equal to a to the k, that's, let's say, element number D, multiplied by 1 minus a to the power of n, which is element number E, multiplied by 1 over 1 minus a, which is element number F. So now you know how to calculate geometric series, and all you really need to remember for the future is you can think about this infinite geometric series, 1 plus a squared, and so on, and everything can be handled from there. So let's conclude with an example, okay? This is going to be a real-world example. Imagine that you're an ECE 421 student, you graduate, you get a nice job, and every year you're going to save and invest $10,000. And suppose that your investments from previous years, they grow by a factor of 1 plus p. P is the growth rate or interest rate, whatever. And a 7% growth rate is plausible. Some of you may invest very aggressively, and you may get a larger P, and you may be forgetting about the impact of inflation, and others among you may invest a bit more conservatively, and you may account for inflation and the standard of living creeping up. So maybe this P could be viewed as, by some of you, as pessimistic, by others as optimistic, but it's plausible, okay? So what is going to be our situation after n years of this regime of saving and investing $10,000 a year and growing the current investments by a factor of 1 plus p every year? So from the first year, the $10,000 were multiplied by, we have n minus 1 years for growth. So we have 1 plus p to the power of n minus 1, multiplied by 10k, of course. Year number 2, we need to multiply our savings by 1 plus p to the power of n minus 2, because we have n minus 2 remaining years. That was the parrot whistling, of course. Year number 3, we take 1 plus p to the n minus 3. And finally, year n, we're multiplying by 1 plus p to the power of, well, we have 0 time left, so that's 1. So overall, putting aside the $10,000, we're multiplying the 10K by a summation over n going from 1 to capital N, 1 plus p to the power of capital N minus n. So that's the amount of time left. But now, let's think about the powers. When n is equal to, lowercase n is equal to 1, capital N minus 1, and when it's equal to capital N, we have capital N minus capital N is 0. So we're summing over the n, capital N numbers from 0 to capital N minus 1. So let's just say that we're equal to change of index to n prime. We're summing over 1 plus p to the n prime, where n prime goes from 0 to n minus 1. As we've seen before, this expression is equal to 1 minus 1 plus p to the power of n. There are n elements in the summation, divided by 1 minus 1 plus p. This could be interpreted as, recall that 1 minus 1 plus p is negative p in the denominator. And in the numerator, we have 1 minus 1 plus p to the power of capital N. But now recall, I can multiply both sides by minus 1. So we get p in the denominator. And in the numerator, we get 1 plus p to the power of n. Is this promising? Is this not promising? 1 plus p to the n minus 1. I may have forgotten the minus 1. So now there's a well-known rule that if you take 1 plus p to the power of something, and p times something is approximately 0.7, you're going to get 2. So if p is 7%, after 10 years, you have approximately 2, but you need to subtract 1, so you have 1 divided by p. After 20 years, 1 plus p, again, 7% might be plausible. 1.07 to the power of 20 is approximately 4. So I took 7%, I took 20 years, and I calculated minus 2.87 divided by minus 0.07. Again, you could add negative signs to both the numerator and denominator. I got approximately 41. 41 times $10,000 is approximately $410,000. So that'll be it. Real world example, what you can do after you complete the course and graduate, and we'll continue with the next module on background next time.